Yes. We start in the mix. Okay, we're resuming the assessment session. It's my pleasure to introduce Pablo Soberón. I was going to present new results about unit-free distributions.
Okay, so first of all, I want to thank the organizers for giving me the chance of giving this talk for the invitation. Got it. Thank you a bit. And also hi to all the friends and you well. Okay, so what I want to do in this talk is to tell you about a couple of new results regarding distribution, but more than that, what I want is to sort of convey why topological methods are actually useful in this sort of process to motivate them. So first we'll go through a bit of motivation of the problems, and then when we sort of dive into the techniques, we will actually go into some new results in here. Okay, so let's start with sort of a broad overview of what I want to talk about today. Here, okay. Okay, so I want to talk about fairness. Fairness in itself is like a combinatorial problem. Because the type of problem I want to talk about is we'll have a bunch of resources. Maybe you have different types of resources, different amounts of each of them. Maybe some of them are divisible. We have here maybe these two things together and we can split them. And we want to divide them against among some number of participants. Okay, so we have our participants, and even our participants they might have subjective preferences. So one of them might value the yellow pieces a lot, the other one might value the green pieces a lot, and we want to divide the resources among two people, or in some cases around k people, in a way that we achieve some fairness range. And what we mean by a fair distribution is also going to depend problem basically. So since they have subjective preferences, maybe we want everyone to get exactly the same value. If everyone agrees that every single person is getting the same value, and so that they can't complain about anything that they receive it or that the other people. And so I want to study when can we achieve such a division, and if we can, how can we achieve such a division? If this is too difficult sometimes, maybe we just want each person to be happy with what they received, but maybe they don't see every piece being valued equally. But that's the other people's part. If I got my favorite piece, I'm happy and I'm working. Okay? And so this is what we would call an envy-free distribution. And so you might imagine that as we relax the definition of fairness, maybe you can increase the number of situations in which you can achieve it. Okay? Now, speaking of resources, many times they're going to come with some geometric data attached in a way that fairness is actually going to be a geometric one. Okay? So what do I mean by this? So instead of giving just a number of resources and you can do any subdivision you want, maybe my resources are constantly plane, and it depends on how I'm going to divide the whole space. I'm not going to be allowed to go in and pick red points and give it to someone, green points and give it to someone else, but I want to sort of have a partition that makes use of this geometric information. Right? So for example, what if I want to cut my space into 3 convex columns and divide this among 3 participants? So this would not be a very fair partition if we value each set of points equally, because this person is receiving only 1 red point and this person is receiving many more, right? But if I continue to do this and I search quite a bit, maybe here I have three convex pieces by two parallel lines, and everyone gets two blue, two red, and two green if the figure actually shows up correctly. Okay? Or maybe we can have a test. We have two participants, and this test contains exactly half of every color class. And so it begs the question, did I get this figure because I first drew the circle and then drew the points so that I would get a position like that one? Or is it true that whenever I give you 3 sets of points in the plane, I can find a test that contains exactly half? And so, depending on the geometric condition that we have, sometimes we can do this per partitions and limitation. And this result of a circle, it's a classic result regarding an extension of the Hans-Sandwich theorem. So, so we have sort of three diagrams. One is the fairness guarantee that we want. Maybe we want anti-freeness, we want a perfect distribution of resources. We are talking the resources we're going to divide depending on the number of color classes of points. If we have points in the plane, it's in a different space. If we have some measures in the plane. So basically, what are we subdividing? And finally, how are we allowed to cut our space to distribute it economically, right? And so you might imagine that this is in some situations you cannot get into a partition, in some situations you can, and this is sort of the big road problem that drives all of the results in this. Okay? In some sense, it's like you're trying to catch two rabbits which are running in different directions. On one side, you have your combinatorial information, the fairness constraints. So how fair can you make a partition? And on the other side, you have the geometric conditions of the partition. In some way, you want the simplest shape to use to get your partition. You don't want to have to carve all the space in a very complicated way. And you might imagine that the more complicated the combinatorics become, the more complex the geometric shape you're using to cut your space happens. And if you try to solve this problem in an efficient way, with catching both rabbits at the same time, I guess it's no surprise in this conference that topology sort of puts up and topological techniques are essentially what allow us to get optimal results in this thing. Okay? And so ultimately, fairness is a topological problem, and I want to focus on why it might be natural to actually think of. In some problems, it might feel like it's very more detached from the problem we're looking at, but in essence, all of the problems we'll talk about have a very deep topological background that is really telling us what the essence of the problem. Okay? And so this is the big goal of explain how topological tools can be used in some partition problems, and we'll do that with some new results. Okay? Before I jump into the meat of the talk, maybe I want to show this picture. So recently, a colleague of mine, Ricardo Campensalo, who works in Aurelia, and I we wrote a survey on mass partition problems, extension from the Hans-Sandwich. Okay? And so once you have a few hundred citations and references, you just ask, okay, so Python just plots the individual days of published, and you get something. And even though you are biased to cite recent papers, I think it shows that it's a growing and active area more than something that's stable, right? So this is something that we found, and I like to show you. It's sort of exciting. And if you're unfamiliar with this area and you want a good resource to read on, using the Pursuit theorem by Chekamatisek is by far my favorite book of the topic. It's really a user's guide to use the topological methods in this. And if you have a chance to read it, I highly recommend. Okay, so let's dive into and talking about topological tools. As you can imagine, we have a wide range of tools. Usually, I like to keep on the left side of this arrow where we have simpler tools. We basically want to reduce things to jump from multiple arguments, directly take some topological results which are known on the shelf and modify them like the Pursuit theorem. Or if you go further down, then you can start using a preference theory, take your favorite index theory and see if it's helpful. So you can go really far in terms of complexity of topology. So let's start with an example that's I talked about geometric data in our resources. So the lowest we could do is dimension 1. And even in dimension 1, we get interesting points for this. So let's start with the first cutting case. Okay, and this is the actual name that people use to refer to this problem. This is not making a, this is not me making a funny name for the solve. But let's take the motivation that we usually see for cutting a cake. So in this scenario, you are cake of returns, and you want to subdivide the cake between 3 nights. Okay, so you're allowed to make a cake with cuts like this. So you're only making vertical cuts in your cake. You might shape them to left to the right, or you're not allowed to do any twisting or anything like that. Okay, so you might identify your cake with the interval 0, 1, and you're dividing this into cake intervals. Okay, and this is what you want to distribute among. So let's just color code them red, blue, green. And if I give you your 3 nights, I'm going to ask them which piece is your favorite. Okay, and each of them, they're going to tell me maybe I want the green piece, I want the blue piece. In this case, this rightmost piece is preferred by 2 nights, so we're not able to make a distribution where they will all happy, right? If we wanted to give everyone their favorite piece, we would have 2 people fighting over one of the pieces. In this case, if we maybe modify or partition a base, 2 of the nights change opinion, and now we get an MVP partition. Everyone gets a favorite piece, and they don't really care what it is. Okay? So the question is there something that's bound to happen, or can I find set some preferences and nights where I can't get an MVP distribution like this? So if I give you 800 guests, meaning that they always want an MVP to them, and I always find an MVP rotation yeah, and the answer is positive for this. It's a classic result by Moodle and Surface. We prove this independently on the same year. That whenever you give me 800 guests, then there is an MVP distribution of them by dividing the interval to a. Very little geometry, right? It's just the pieces have to be intervals. That's the only geometric constraint that I have. And the conditions of the guests are they have to be found whenever I present a cake to them. Among the favorite pieces they tell me, they have to tell me at least one non-empty piece. And the other one is that the preferences are always closed, meaning that if I give you a sequence of converging set of cuts, and for example, night number 1 always likes the 7th piece in every cut I'm presenting, in the limit, they also like the 7th piece. They cannot change their mind in the limit. Okay? You can also replace this by the preferences that all got to be open, which has a single flavor, and with these conditions, then you always get it. As an example, if I give you a smooth probability measure mu on interval 0, 1, that would be like the preferences or the way one of the nights values the cake. They could always choose the largest piece, the piece that has the largest measure, and this is an example of a good set of guesses. Strongquist and Moodle, they actually used it, they solved it for measures, but for general conditions like this one, it's also not. Okay? So let's dive into this one. So let's try to formalize this a bit. So if I call x1, x2 to xk the lengths of the pieces, the conditions in that is that these numbers are non-negative and they add up to 1. So they're really parameterizing a sequence. And the vertices, example, this vertex here, corresponding to the position 1, 0, 0 means that the red piece is everything, and then we have an empty piece and an empty piece. Okay? And so on, the blue one is just telling me that the middle piece is everything and the other piece is empty, and so on. Okay? Now, how does this play with the preferences of people? If I give you a partition, and I present it to the right, they might tell me, so in this case, they might tell me, oh, maybe piece number 1 is the biggest, so that's the one I want. So I'm going to color the vertex this point here, depending on the preference of this person. Okay? And if I change the partition and now I prefer the big piece, I'm going to color it. Okay? So the preference of one person is really a covering or a coloring of this k minus 1 dimensional sequence. And so if you do this, for example, this with the preference of this nine, we always want the biggest piece. So they're just looking at which vertex they have the closest and they get this distribution. But other lines might have other coverings. So what's interesting here, this is what we call a KPN cover on simplex by Master Kratowski and Maskevich. And it's basically a k-tuple of sets, one for each vertex, or one for each vertex, so that and this every set is closed. This comes from our preference being closed sets. And this condition for every case in my simplex, the face is contained in this union here. So for example, if I look at this segment between the red and the blue, this segment here is when the last coordinate is 0, meaning that the green piece is empty, so you never want the green piece. So you have to cover this with the blue and the red. Okay? And the same thing for the other segments here. So that's really what this is saying. And on the level of so what they actually put is that, for example, if I give you a set of covers that does this, the intersection is not empty. Something like this. This is not an accident, it's always something always going to happen. And this is basically saying if I give you a cake, it's going to be a partition where you don't care which piece you take, you value them. And so the preference of one person is a KKM cover on the simplex. So if I give you 3 people, what I want is 3 KKM covers. And you might notice that back here, the preference sets don't even have to be connected. They just have to be closed and satisfy this phase of the given site. Okay. And so what we want ultimately is to have a partition that we can distribute among the people, like this one, which happens to be on the green set for this guy, on the red set for this guy, and the blue set for this. So we give this person the green piece, red piece, the blue piece, and they are happy with their distribution. So the question is, when I give you KKM covers of this K9 of the dimensional simplex, we always get something like this. And this was proven by David Taylor in 1984. So this came after Woodland Strongest because it works on the level of KKM covers, not just those that come from preference dimensions. And the big theorem is that one. So you get one KKM cover for each person. Okay. And then there's going to be a permutation that tells me who gets which piece. So this being non-empty means that you have only that section. And piece number 1 is going to go to person pi 1. Piece number 2 is going to go to person pi 2, and so on. Okay. So I will dive into the techniques to do something like this. But before I do that, maybe I can talk about this beta approach to the front. This is related to motion planning, where you have maybe a robot and want to decide how it moves. Maybe you have a robot board and you want to make algorithms to decide how it's going to move and respond to the tasks. And the way you approach problems like this is you can parameterize the space of all possible positions of your form. And then you find a fine triangulation of the space. And now you have a finite problem where you want to decide how you're going to move along through the sequences in this triangulation, right? In this problem, you can do something like this. Let's say you want to do the KPN third. You have your KPN for cover. So I'm going to triangulate my space and define triangulation here. And my KPN cover induces a coloring on the vertex of the triangulation. If you're in a green piece, you color it green. If you're in a red piece, red, and a blue piece, blue. If you're in many of them, you just choose one and color it that color. And then what we call a Sperner coloring of the triangulation. And instead of looking for a point that's in common to all regions, I'm going to be looking for a triangle whose vertices have all colors. Okay. And if the triangulation is fine enough, maybe that makes you happy and that's enough. And the way you can do this is by pathfinding arguments, where you move up among the simplexes and notice here that I'm only moving through blue-red dots, blue-red segments, and what I start from the outside, and when I get stuck, I get exactly. And this actually works with it. If you go in and then go out and just try to go in differently, there's a small induction curriculum that is actually very simple and nice proof of what they do here. And with more centric subdivision, you can even get Gale's result this way. So what I wanted, or what I read about this, was a framework to this approach doesn't work, or where it breaks down the process. Okay? And just to mention, there are many versions of the cake splitting theorem, where you want to make it algorithmic, it's a big problem. Polytope, you don't have to do things of synthesis, you can do general polytope and generalize the usual, the natural way, and everything works out nicely. But you can have some of your guests obtain the preferences in advance. But there are many variations. You can relax the hungry guest conditions. And that's actually one of the things that we did right here. So in this new version, you're going to divide your take up with 3 people. But you have 4 guests, right? So if one of them are hungry, you just take 3 of them, divide the take between them, and that's it. But now your guests are picky eaters, and sometimes they want one. So in the setting of taking in covers, maybe they look like this. Okay? So you have here a person that wants, say, 45% of the cake. If you don't offer 45% of the cake, they just reject everything. Or you have this person here who wants the smallest piece, but if anyone gets too much cake, they just refuse to take any piece. Okay? They won't participate in that subdivision. Then in this case, if I overlap this preference with this preference, it turns out to be a KKM over of simplex. So they together they act like a other person, and with this other 2, I'm able to find a subdivision. Right? If I take these 2 people and ask them, I make a part of the cake and I ask them, does any of you want cake? At least one of them will tell me that they do want cake. Okay? And that's actually the condition that we need here. If I have n guests and k pieces, if every time you ask n minus k, you have 1 guest if they want a piece, at least one of them wants a piece, and then you can find k people and the subdivision that partition by k that makes everyone happy. If everyone wants a non-empty piece, and everyone gets their favorite pieces. Okay? And this number n minus k plus 1 is optimal, because if you have this number of k guests that never want cake, you have almost k minus 1 people remaining, and you can do the subdivision to k pieces and make everyone happy, because you don't have enough. So in this case, this person might not be hungry and this person might not be hungry, but whenever I take 2 of them, I'm going to overlap. Okay. So let's dive into the technique to do this. I keep clicking this. Remember, it doesn't do anything. Okay, main topology. So how are we going to do this? So say you take a point in the simplex, for the moment take KPN proper, we're not dealing with our APs yet. And we're going to make a function. So I'm going to look at the distance to the complement of A1 of my first pocket, right? So here, this is embedded in port N, so we can, so this is it. And for example, if this is my first vertex, it would be the distance I have to walk out to get out of the real region. Okay? So this would be a positive number. For the next one, the amount of time to walk to exit the real region would be 0 because I'm already outside the real region, and so on. Okay, so I just look at the distance I need to walk to exit at least one of the regions. And I don't like point A, but since this was a cover, at least one of these distances was positive, so I can just divide by the sum. And I get this function from the simplex to the simplest. Okay? And this is a really nice observation. If I give you a face of the simplex, the image of the face is contained in the face. Why does that happen? If I'm in this phase here, for example, this is the region where the green piece was empty, so I was never going to put the green piece there. So I have to walk 0 distance to exit the green cell. So if the first coordinate was 0 here in the image, the first coordinate is going to be 0. That's exactly what it is. Okay. And the cool topological fact here is that if I give you a function from this that's continuous, even on a polygon, it doesn't have to be on this simplex, then it's going to be a projected. Now, the reason for that is that this map sends the boundary to the boundary. So the facet has to go to the point of the facet. So restricted to the boundary, this is a function from a sphere of dimension k minus 2 to a sphere of dimension k minus 2. So we can compute the degree of this map, and it turns out to have degree 1. And if this was not a surjective function, by another argument, you can show that the degree of that encrypted map should be 0, and 1 is not 0. So we get the surjectivity. What we actually want from this surjectivity is to keep the variance center in the map, meaning that these coordinates have all got to be equal. Because if they don't have to be equal, well, at least one of them was positive, so they were all positive. So this means that you were in region A1, A2, A3, and so on. Right? That's a proof of the Pavilion theory. That's a complete proof of the Pavilion theory. So now we want to do this for our NV3 distribution with PQ. So what we're going to do is we're going to take our covers, or almost covers of our simplex, and we're going to make a matrix. Okay? Each column is going to be the function I told you about for a particular person. So I get the distances here, and then I normalize it so that the sum is equal to 1. I take the distances with that one, and do the same thing, and so on. Okay? So this is a matrix where the columns are all will have sum to 1. Maybe if I have it one here, the column must be zeros, and that columns a bit of columns. I will ignore them for a minute. We make a column for each cast. We normalize each column that we can, so they sum to 1. And then we look at the sums of rows. So we look at this new vector here, the sum of this, the sum of this, the sum of this. And that function, and then we can normalize this vector here. That satisfies that f of sigma is containing sigma. So you can just check that it does that. So we can make the sums of rows equal. And then you go back and say, okay, you have to be really careful because you can't do this every time. So if you go back and then you do some arguments, which I won't go through now, what you get in the end is a matrix with these properties. So the sum of each row is the same. This is what we got from our degree already. The sum of each column is at most 1. You sort of almost got what we wanted from this column, but at least k column sum exactly to 1. And think about the case n is equal to k. Okay? N is equal to k means you have a k by k matrix. All the sorts of rows are the same. Every entry is non-negative, and k columns, so every column sums exactly to 1. This will be a doubly stochastic matrix, which is the perfect combination of permutation matrices. So in this case, we get almost something almost like that. We can find k elements in different rows and columns, which are positive. And that's the description that we wanted. Because this being positive means that this person wanted piece 1. This being positive means that this person wants piece 2. This being positive means that this person wants piece 3. Okay? And that gives us the description. So we make this construction. We have this degree argument that tells us that some we get this nice matrix. And then we use a pay-to-pay algebra to get this or here and get the distribution that we want. Okay? Good. So now let me move on to the second one. Oh, and we had this issue with some issues with the continuity of our functions, and probably that you can fix it. So I won't go into the details of that. I want to convey the main idea or the degree of it. So now dividing sandwiches. And this is the classic result in the area, the reason why everyone solves the results after some item. So this is, if I give you two regions in the plane, there's always a straight line that does exactly that in terms of area, what's on each side. Okay? And we can think of this as the pan, this is the cheese, so we're making two sandwiches for our best. And this works in 5 dimensions. This is the pan sandwich theorem that if I give you d finite measures in RD, there's a hyperplane that simultaneously has each. This was proven by Banach in 1958. I have an asterisk here because the paper that appears is from Hugo Steinhaus, but he says this is not my proof, it's Banach, and he even all the way back then, people already knew that these were topological transcendences. And the topological rule that goes here is the pursuit answer that every continuous odd map from and this should be reversed, this should be SD to RD, some sort of other. If I map a d-dimensional sphere to a d-dimensional real space, then there have to be two antipodal concepts. Or if I have an odd map, meaning that f of x is equal to minus f of minus x, then you must have the zero. So the symmetries of this here is really what's driving the existence of the zero. And if you think about this is a space with an action of Z2. This is a space with an action of Z2. So another way of stating this is that every continuous C2 equivariant time. So doing the action, then the function, same thing with the function and the action, must have one. Okay. Okay. And D measures is actually optimal. If I wanted, for example, 3 regions in the plane, I wouldn't be able to have 2 of them and guarantee that I'm also planning this one. But again, more complicated problem, more complicated regions, and maybe you can solve it, right? So maybe with a wedge, we can solve something like this. And so what do I mean by a wedge? One line with exactly one term, the intersection of 2 lines. And this is a result from surprisingly recent. If I give you 3 measures in the plane, there's a wedge having each. And just as the half sandwich result term has a high dimensional version, there's one here, which I also find surprisingly recent. If I give you now d plus 1 measure, so one more than the sandwich, there's a wedge intersection of 2 half spaces that cuts every single one. And this result of Patrick Schindler is also optimal. You can do this with d plus 2. So maybe let's quickly prove this one. Okay. And this is a proof that I had with a youth that actually she was an undergraduate student at the time and came to work one summer at one college with me. So what we're going to do is to take a dotted line in the plane, and then I'm going to place the plane in dimensions 3. Okay? So think of it, this works in pair dimensions 2, but here we have a plane in all 3. We have our dotted line here, and then we're going to make this surface with 2 half planes going up. Okay? Now, if I had regions on this plane, we can project them up, and I would have the measure in dimension 3, this blue surface. I have 3 measures in dimension 3, we can use the half sandwich curve. So we just get a plane that cuts everything into half. We have to be a bit careful with the choice of this line. We have to translate it maybe a bit so that we guarantee that when we do this here, the halving hyperplane is not either of these 2 features. But that's not really an issue. And so you intersect it with the plane, and when you project back, you get the wedge that cuts everything without having to do anything. But when you do this, you might notice, well, you had some degrees of freedom for the line, the dotted line you were choosing, right? You chose any direction and translated it until you hit sort of a sweet spot. But what if we rotate this line? So what was happening here? When we found our wedge, actually the vertex has to be on the line, right? You get a bit more information about this wedge. And think of a person walking along this line here. When they hit this wedge, they see an obtuse angle in front. And then we start rotating this line, getting our wedge every time. When we do 180 degrees, and we're walking out here, we get back to the same wedge we started with. But now when we're walking here, we see an acute angle. So we went from an obtuse angle in front of us to an acute angle in front of us. So either at some point we saw a straight wall in front of us, a big straight line, but that would mean we have a line having these 3 features, which might not exist. Or at some point we're not able to measure this angle, which happens when the 2 lines will actually parallel to each other. So the vertex goes to infinity and so and so this is one of the results we put that I give you d plus 1 measure more than a wedge. You have had 2 hyperplanes so that the region between them contains exactly half. And so you say, okay, that's exactly what we told you about, you can formalize it, but then you run into a lot of issues. Because when I'm doing this rotating argument, whenever I'm finding this cut in dimension d plus 1, I have no guarantee that it's going to be unique. And that's a problem. And as I'm moving along, I have no guarantee that it's going to be moving continuously, which is also an issue. So you have to sort of deconstruct the proof of the Van theorem in this bigger space and sort of reinvent the wheel. Okay? And just as the Van theorem is proven with the Borsuk-Ulam theorem. Here there's going to be a topological tool, which is similar to the Borsuk-Ulam theorem, but it's a bit more complicated. So our group is now Z2 to the K plus 1, and we have these workable spaces here. In here, we have a direct product of many real spaces, and now I did get it right. The sphere is on the left side. So we have a sphere of dimension D, and here is steeple manifold of orthonormal K frames. And I won't go too much into it. I just want to convey the idea that the complexity of the topological results explode even if we didn't. Okay? We have a much more complicated group, and we want to study the map from these spaces to these spaces. But we get the conclusion very similar to the Borsuk-Ulam theorem. A zero here is going to tell us that we have a quotation. It's going to tell us that the hyperplane we get in the end is going to be parallel, sort of measured by the first few real spaces, and then it's going to tell us that we are taking our dimension sufficiently. That's, I think, the last one. And in some sense, so I can't resist to give this quote by the reason that groups of individuals or non-group actions. And this is exactly what goes on. Every extension of the Ham sandwich theorem has sort of a topological platform for the symmetries of your space of the symmetry. But rather than go into the details of this one, so I mean, maybe I can give you the gist of it from a broad perspective what happens here. The idea is we want to parameterize the space of partitions with a sphere, with this steeple manifold, with some other thing, with the Arcadian covers of synthesis. And then we want to find the work to value the fairness of the partitions. Maybe the matrices we were constructing, this function we're working with. And we would use our column with topological forms. So we get either the geometry and the combinatorics, which are once we identify the topological form we want to work on, this is a one of our topological form we just want to figure out when we have zeros for this map, when we discover stuff we want in this section. So this we talked about earlier. We're basically building a dictionary with partitions of more detailed topological. And there's a really nice mix of partitions that I want to have my actual second example. It's made of convex partitions. You might recognize this picture because it's just right on the side. Right? This is the atrium that we have here. And a convex for this regions, you might look into them, not all of them are convex. But the idea is to split 14 into regions which are convex sets and interior for parallelization. Okay? And there's a naturalization of the Ham sandwich here. If I give you a number n and give you measures in 4D, then there's a partition of 4D into n convex pieces, so that each piece is exactly 1 over n of each direction. Think of the case n is equal to 2, that's the Ham sandwich here. The only way to split 4D into 2 convex pieces is with a hyperplane, and that's exactly. Okay? And this, I put it in 2012. In 2014, there were 2 other proofs, which were mostly at the same time as this, but they took a bit longer to go through the review process. And they were motivated by some similar points. So what I want to talk about is an NV3 partition of this result. So here, if we think of every measure as the preferences of one person, they all think that the partition is completely fair. Everyone is getting the same value. But if I want an NV3 partition where everyone just wants to get the maximum of their measure, maybe I can add much more measures than. And this is the result that's sort of fresh out of water. Before I talk about this, let's sort of compare the two types of results. I have equipartitions, everyone thinks everything has the same value. This was the classic result of the cutting. The number of participants is really bounded by the dimension or the function of the dimension. Here, even in dimension 1, we have a number of participants. And then you have the different topological tools. What I've done for this here. Before I jump into the algorithm, this is also related to political science. You can relate this to gerrymandering. So gerrymandering, people who do this are very used to this term. The idea is that the resources now are going to be objects. Okay? So you are going to make districts, and every district is going to elect a leader, and so you make a Congress district. And depending on how you make the districts, sometimes, for example, in this subdivision, you have 7 districts with 7 people each, and everyone is won by the blue party. But in this partition here, 7 districts, 7 people each, every single one of them is won, but not every, the majority is won by the red participants. And neither of these situations is what I would compare. Because here you're completely drowning out some people who have like 30–40% of the votes. And on this base, you have a minority getting a majority. This is something that doesn't really happen in Mexico because we have the United, which is a whole other mess in its own. But in the US, since states can redraw the districts, this actually happens quite a lot. There's a ranking of the most gerrymandered counties where people are really, I mean, forming out votes in some regions. And this is an issue that's very recent. But if you do this with this convex partition with all dimension, you could have perfect gerrymandering with convex regions. They would look very nice, but you would be doing sort of the worst case scenario. So you have to be a bit careful about this. Okay, so what is the NU3 version of this? So now I'll start with a policy measure already. And it's for the other d minus 1, I'm going to replace each of them by an n tuple of measures. Okay? And what I want is to find a convex partition for d into n pieces so that mu is split into n pieces of the same size. So mu is happy. And for each of these n tuples, that partition allows me to do an NV3 distribution. Okay? Or ideally, I would want d n tuples and just do a simultaneous distribution for everyone, but we couldn't do that one, we have to stick with at least one measure here. Okay? There's some space here. We need n to be a prime power for our group. And this is more a consequence of the topological tools we're using than in SST on the policy. Okay? So I want to talk about this before. And just as a side note, if every measure on this n tuple is the same thing, so for the first n tuple, we're just repeating one measure n times. For the second n tuple, we're just repeating one measure n times, and so on. And every subdivision on that has been an equipartition of that measure. So you recover this result for prime powers. And this result for prime powers is like this result for anything by a subdivision of it, which doesn't. Okay? So it doesn't generalize the previous result. Christina, you is another good student at MIT who I work with this one. And so how do we approach something like this? Well, we need a super type term. And so let me tell you about the two spaces which are involved. The first one is the configuration space of n points moving. This is just the n tuples of n different points in order. And the second space, what I call W to the n minus 1, this is just the real space of dimension n minus 1, but I want to do this as n tuples of real numbers, so sum is equal to 0. Okay? The reason I want to look at them this way is because both spaces have a nice action of the symmetric group on right? If I remove the entries here, and I remove the entries here, I have a nice action of this. And the big topological tool is something that Lagovich and Ziegler proved, they should say 2014, when they proved this result about convex equipartition. If I give you a continuous Sn equivalent function from this configuration space to the T minus 100 processes, it has a 0. For n is equal to 2, this is a very complicated version of the Superman theorem, but for bigger n, this is really easy. And the way that this is the configuration space, it parameterizes the space of convex, it parameterizes a subspace of the convex equipartitions of one measure. Okay, so you're picking out of, you pick your initial measure, and this is an equipartition, and for the other d minus 1 measures, sort of can use this to tell you that at some point the zero here gives you an equiposition. Okay? So we wanted to use that, but instead of having an equiposition for d minus one measure, to use this so that the d minus one n tuples of measures we were working with, we could do an entry through partition. And just as before, the way we do this, so I give you a convex partition or the that n tuple of measures, we're going to make a matrix. Okay? So I look at the, for example, for mu j, I look at the maximum value that mu j of the regions can have. And the entry here is going to be this quantity, if this is very close to being the maximum, maybe minus epsilon here, or zero for the maximum. So the entries are non-negative. And then I can, at least one entry is going to be positive because whenever I put the maximum, I get epsilon here. So I can normalize the columns so that they sum to 1. And now I can fill the sums of rows, just as before. Okay? So what the algorithm secret tells us is, so here we have a vector in O n. We don't quite get a vector W n minus 1. So instead of getting a 0, we can make this column have equal entries. And since we can do this d minus 1 times, it tells us that if for our d minus 1 n tuples, we do this to make it for d minus 1 matrices, we can make each of them double stochastic. And just as before, in this case, we don't have to do anything, we just involve Berkowitz theorem for double stochastic matrices. We can have a permutation, so picking an element from each row without the being balanced, so that they are positive. And being positive here means that we are very close to the maximum, right? And finally, take x equal to 0 and make sure you didn't break anything. And once you do that, I get the result. Okay? Then we also so we had a bunch of results of this slide. The big broad question that's sort of in my mind these days is if you give me a mass rotation result, like the sandwich theorem or the convex equiportation result, which of those have entry-free generalizations? How close can get to replacing every measure by an intuple and getting entries? Here we got almost exactly what we had before. We had this additional constraint on, I never mentioned why we need the trap out. In this result, the total result, we need n to be a trap out. And this result fails if you don't propose that. It doesn't mean that the contract samples for this translate to this product, but it means that you either have to know more about the precise functions you're constructing here, or you might be able to take that contract sample here and really make it. So this is sort of the broad one that's in my place. And I think that's as far as I wanted to get to today. So, okay. Are there any questions?
So perhaps the question doesn't make a lot of sense, but is it possible to do like something analog but for graphs? So instead of having like convex partitions of the plane, you have like a color graph and you want to, for example, cut the graph into pieces such that each piece has like the same color or something like that. And then, I mean, I know because I work a lot with configuration spaces of graphs. That's why I have a bit of asking.
So in general, if this works, then you get to pick the space you're working on. So if you, when you're making this sort of partitions, if you have a nice topological space that controls this, then and you have nice symmetries on the space, then this symmetry. Some of these techniques are also used to down chromatic number of graphs and type of graphs, and that's another story, but it's also in Lattice's book. That's also
Any other questions?
There's a problem in the nuclear industry. I noticed because my brother works in it. We talk about this all the time, where they're looking at nuclear fuel rods and they have a set of reactors. And the problem is you need to be able to distribute these fuel rods to the reactors so that all of them basically get the correct piece of cake. Similar, these are discrete objects, but they have, this fuel rod may have more fuel than another. And this reactor may be burning fuel at a slightly lower rate because of how the fuel rod was created. So I was wondering, have you thought about applying this as like sort of an optimization problem for things like this, like nuclear power plants or energy distribution or things like that?
I haven't heard about this one before, so, but I would be interested to, hear about it.
Thank you.
Any other question? Yes, thanks,